Today we are going to discuss circular motion. Here we'll do what is circular motion, what is uniform circular motion, why we need a force from outside to act on a body which is kept in circular motion. What are the different examples for the external forces acting on the body which is there in circular motion. What is the direction of this force in uniform circular motion? What are the different types of such forces there? We'll also discuss what is centripetal force and what is centrifugal force. We will derive expression for centripetal acceleration acting on a body in uniform circular motion. We'll also discuss the different cases, what we get there, and what are the different forms of such expression. So all these we'll discuss in today's discussion. So let's start with circular motion. Circular motion we define as if a body is constrained to move along the arc of a circle, then it is said to be in circular motion. Like you have a body which is moving along the arc of a circle. This is suppose the circular path. And if the body is moving from one point to other there, or from here to here, in that case we say that the body is in circular motion. It's not necessary that it should complete the entire circle. Even it is describing a small part of it. In that case, we'll say that it is in circular motion. And then we have another term that is your uniform circular motion. And uniform circular motion we define that if a body describes equal length of arc of a circle in equal intervals of time, no matter how small its intervals may be, it is said to be in uniform circular motion. That means we are taking that the body is describing equal length of the arc of a circle in equal interval of time. Here, suppose the body is moving from this point P to Q, and in moving through this length, suppose it is your delta L, and the time taken is suppose delta T. If it moves from some other points, like it is your R and S, this length is also say delta L. And here also it is taking the same time delta T. So then we'll say that the body is moving in uniform circular motion. Wherever we take, it should be the same length delta L in same duration of time delta T. Of course, if we now take suppose the length which is your delta L by 2, then this particular length must be described in time delta T by 2. So then we'll say that the body is in uniform circular motion because we have said that it describes equal length of the circle in equal interval of time, no matter how small intervals may be. We can go on decreasing this time gap there. And whatever be the small time gap which we are taking, in that it must describe equal length of the arc at different points there. Then only we'll say that it is in uniform circular motion. There is a very important point in circular motion that to keep a body in circular motion, a force from outside is essentially needed. If there is no force acting from outside on the body in circular motion, it will never move in circular path. So force is essentially needed. You take any example of body in circular motion. What can we take the examples? It may be the motion of the planets around the sun. So there the external force is gravitational force of attraction. If you take motion of the moon around the earth, in that case again it is the gravitational force of attraction that provides the necessary force from outside. If you take the motion of the electron around the nucleus in case of an atom, here it is the electrostatic force of attraction that provides the necessary force. Similarly, if you take a stone, tie it with a string and whirl it. So again the stone is moving in a circular path. Here tension in the string will provide the necessary force. You take any example of bodies in circular motion, there must be a force from outside which will act on the body, then only it will move along the circular path. So force is essentially needed from outside. Now, why that force is needed? Because if the force is not acting on the body, then it will move along a straight line path in conformity with Newton's first law of motion. Because in absence of force, it will move in the straight line path. So a force is essentially needed, which will deflect it from its straight line path, and it will keep it on the curved path along the arc of a circle. Let's take one example. Suppose you have a body. This is the circular path which we expect a body to execute. Or this is the circular path which we want that the body should move or follow. Suppose the body is at this point. It has been given any velocity. In that case, it will move along a straight line path like this. It will move tangentially. So after some time, the body will come to this particular point in conformity with Newton's first law of motion. So a force is essentially needed there because that one should deflect that one, and it should keep the body not at this point, but somewhere on this point on the curved path. The moment it reaches here, now the tangential velocity will act in this direction. So after some time it will reach here. The force must deflect it so that it reaches this point. So a force is essentially needed at all instants so that it can deflect it from its straight line path and it can keep it along the curved path of the circle. So this external force is must for a body in circular motion. If the force is not there, it will move in the straight line path. So that is why we can say that the force is essentially needed for a body to keep it moving along the curved path. You can take one more example. Suppose you have a toy car, battery operated toy car is there. If we keep it here, and suppose I have drawn a circle on the floor or on the surface on which that toy car is kept. If you just release that toy car, it will move along the straight line path. But if you want that it should move along this curved path or circular path which we have drawn, then we'll have to deflect it at all different instants by using our hand, so that it can be moved from this point to this to keep it along the curved path. So here our hand is exerting force on that toy car, and this is exerting external force, and it is deviating it from its straight line path to move along the curved path. Whatever work our hand is doing here, it is just basically applying a force there on the body. Similarly, for all other cases also, there will be an external force acting on the body to keep it moving along the circular path. So that force is essentially needed there. It may be in different forms there. You can take that toy car, which we are taking here. This is attached with a string, and the other end of the string is fixed here at the center. If you release it, in that case also this toy car can move. Here we don't need to deflect it by our hand. But in that case, the tension in this string will provide the necessary force to keep it moving along this path. So that force will be provided now by the tension in the string there. Suppose for the toy car, we are assuming that it is following an anti-clockwise movement here. So if it is an anti-clockwise movement there, in that case, left wheels will be the inner wheels for its path, and the right wheels will be outer wheels. The size of the rear wheels or left wheels there will be smaller in size, and the outer one will be of larger size. So now if this toy car is moving, in that case, since it is two wheels, the front two, they are connected by its axle. So as the axle is rotating with the same speed, angular speed there, so the wheels will also rotate with the same angular speed. But as their radius are different, in that case, they will describe circular path of different length. Because there, the inner one will be describing a circular path of a smaller radius. Outer one will be describing the path of larger radius. And this is possible because if the wheels are there of a different size, then this is possible. So in that case, you are not visibly applying any force there. That is, the tension is not there. We are not deflecting it by using our hand, but still, due to its inclination, a component of the force will be there acting on this, which will provide the necessary force there for its circular motion. So you take any example of body in circular motion, there will be definitely a force acting from outside, which will put the body in circular motion. Once we have said that a force is essentially needed to keep a body to move along the circular path, what is the direction of that force? So let's take the case for the direction of force in uniform circular motion. Let's assume we have a body moving along the circular path with uniform speed. Suppose the mass of the body is m, and it is moving with the speed v. So at any particular instant, when it is at this particular point, the velocity will act tangentially. So this is the direction of its velocity at that particular instant when it is at this point. Here, this is suppose the center of the circular path. We assume that there is a force F acting on the body, and this force is at an angle theta with the tangential direction. Remember, the body is in uniform circular speed or in uniform circular motion. So in that case, it is moving with constant speed. But as the particle will be moving along the circular path, at different points, its velocity will be in different direction. So velocity will be changing in direction, not in magnitude. Magnitude will remain same because it is moving with uniform speed. So here, what we do, we take the component of the force along the tangential direction. So that force will be F cos theta. So this is the component of force in tangential direction. How much is this? This is F cos theta. So what will be the acceleration in tangential direction? This will be F cos theta by m. This is the tangential acceleration. As the body is in uniform speed, so tangential acceleration will be 0. So in this case, tangential acceleration, this is 0. So in uniform speed or in uniform circular motion, tangential acceleration is 0. Now, if this is 0, then what does it implies? F cos theta by m. This is 0. For this particular term to be 0, the conditions are either f should be 0, then we'll have this F cos theta by m 0, or we should have m infinity, then also it will be 0, or cos theta is 0. So if any of these conditions are satisfied, then this will be 0, or more than one condition is satisfied. But at least one of them must satisfy this relation. Now let's see, can we take F0? That means no external force is acting. Obviously, this is not possible, because if the external force is not acting, the body will not move along the circular path. Force is essentially needed. So we cannot take F0. Can we take m infinity? If m is infinity, mass is infinity, force is essentially needed, so you will need infinite amount of force to put it in motion. So again, getting infinite force is also not possible. So this is also not possible. Moreover, we have many examples of bodies in day-to-day life which are there in circular motion and their mass is not infinite. So obviously this m cannot be taken to be infinity. Next is your cos theta is 0. Now, can we take cos theta 0? Remember, f cos theta by m has to be 0 as the tangential acceleration is 0. This will be 0 if either f is 0 or m is infinity or cos theta is 0. If any of these is satisfied or more than one, f cannot be 0, m cannot be infinity, then you have no other option but to accept this. Because only if this is 0, then this one will be satisfied. So that means we have to take this. And if you take cos theta 0, that means what does this theta indicates? Pi by 2. That means this force will act at perpendicular direction to the tangential direction, or it will make an angle of 90 degree with the tangential direction. So 90 degree to the tangential direction basically means it is in the radial direction. So the force will act radially. From the radial direction, there can be two directions. One directed towards the center, that is the radial direction. One will be away from the center. So in that case, we have two directions. So we term there the force which is directed towards the center, that is called as the centripetal force. Centripetal force. And this is called as the centrifugal force. So this is your centripetal force, and this is your centrifugal. That means a force which is directed towards the center of the circular path, that will be called as the centripetal force, and the one which is directed away from the center of the circular path, that is the centrifugal force. We'll do in detail what does this centrifugal force is there and what is its significance there. This is why it is called pseudo force there. Okay, and the centripetal force will be definitely required for keeping the body in circular motion. Okay, so this is the direction of the centripetal and centrifugal force. Magnitude wise, both will be equal. Centripetal force and centrifugal force both will be equal in magnitude, but they will be acting in opposite direction there, because one is directed towards the center, other is directed away from the center of the path. Let's consider a body of mass m moving with uniform speed v along a circular path of radius r. Let's assume that this is the circular path of radius r and its center is suppose at point O. Body is moving along the circular path with the speed v. So when it is at the point say A, its velocity is acting in this direction v1. Remember, magnitude is constant, but as it will have the different directions at different points, so velocities will be different. So suppose it is point A, and after suppose a time delta t, it reaches to another point, suppose it is your B, and at this point the velocity is v2. This is the point. Here we can assume that the position vector of this point is r1, that is of point A, and that of B is suppose r2. And it is describing an angle delta theta at the center. Obviously, if I just represent this v1 and v2 also in some other diagram, at this point of v1, suppose I sit here, let's suppose that this is your v1. We have just drawn line parallel to this to represent it. This is your v2. So that means v2 I can represent again by a parallel vector here, and this is your v2. Now, if this angle is delta theta, obviously the angle between this v1 and v2 will also be delta theta. Why is it so? Because if suppose you produce this one in backward direction like this, This is acting tangentially, so that means this angle is 90. This is also 90. If this angle is suppose your delta theta, this is suppose your point theta, obviously this one will be 180 minus delta theta. This particular angle, 180 minus delta theta. So how much will be this particular angle? This is definitely delta theta, which is the angle between V1 and V2. So this angle we can write it as delta theta. So that is the angle between V1 and V2. So suppose I represent this one as the point P here. And this time, if I take this one as another vector, this is suppose your delta V. This is suppose your point Q, and this is suppose your point R. Also, here what we can take, that if I suppose take this one, this is your R1, this is your R2, I can take this one as delta R here. How we are taking this? Suppose we take in triangle PQR. If you use laws of vector addition, in that case, PQ vector plus QR vector, this is PQ vector or PR vector. This is PR vector. PQ vector plus QR vector, that is equals to PR vector. So this is your V1, this is your delta V, and this is your V2. So what we can write for V2? This is definitely V2 minus V1. That means this represents your change in velocity. And if you consider here also, if you consider this OA vector plus AB vector, this is your OB vector. That means this is your R1 plus this is your delta R, this is your R2. Obviously, delta R vector we can write R2 vector minus R1 vector. So here we have got one relation that delta V will be basically change in velocity, delta R will be the change in the position vector. So here one more thing we can notice from these two triangles there, and for delta theta we can write it as delta V by V1 magnitude or V2 magnitude. This is your delta V by V, as V1 magnitude is same as V2 magnitude, which we have taken it as V. V we have assumed that it is the speed with which it is moving along the circular path. That is the uniform speed. So this is one relation. Also, and delta theta we can also get this as this delta R by R or R1 vector, you can say, that is equals to again delta R by R, as R1 vector magnitude same as R2 vector magnitude, and that is equals to R. So we can take this relation. Suppose I call it as equation number 1, and this is the equation number 2. What we have done, basically we have taken this angle delta theta. For that it is arc by radius. So for a small angle, because here of course all these will be applicable when you have taken that when delta theta or delta t tends to 0, delta theta will also tend to 0. That means it will be very small. And if the angle is small, in that case arc length will be nearly taken as the chord there. So in that case we can take this one as the chord value nearly equal to the arc which would have got. So this is the condition under which we can get this relation. Using equation 1 and 2. So from equation 1 and 2, what we can get? We can get delta V by V equals to delta R by R, or delta V will be V by R, delta R. Suppose we divide by delta T. So dividing by delta T. So this is your delta V by delta T. This is your V by R, delta R by delta T. This is the expression which we get, delta V by delta T equals to V by R, delta R by R. Now what does this will represent? This will represent average acceleration. This will represent average velocity. So now if you want for instantaneous value, in that case we'll have to take the limit for these delta T. Because if the average value you are taking and you are taking delta T tending to 0, then that average value will turn to instantaneous value. So if I take the limit and we take delta T tending to 0, then it will represent the acceleration. This will represent the velocity term there. So if you take the limit, it will be like this. And now this will represent the acceleration. This is V by R into V. Ultimately, this is your V square by R. And what is this direction you see? This is your directed in this direction, V1, V2, and this is the direction. That means here it will be in this particular direction towards its center. Also, you see the displacement delta R which we have taken, it is in which direction? This direction. And this one will represent the direction of the change of velocity. So this will also indicate that these two will be in perpendicular direction, because we have seen that the velocity will be acting tangentially. Here also you can see if you are making this delta theta small, when delta T will be tending to 0, in that case this direction will almost become tangential at the point A or B. Similarly, this change in velocity direction will be along the radial direction. So that change divided by the time duration, that will give the acceleration. So this will be the radial acceleration, or we call it as the centripetal acceleration for this case. And this will be the speed there. So this tangential acceleration or radial acceleration or centripetal acceleration we can write it as your V square by R. This is the expression for acceleration or centripetal acceleration on the body in uniform circular motion. And its direction will be directed towards the center, that we have already seen here. Centripetal acceleration, we have got it as G square by R. It can be given in other forms also, like it can be given as your omega square R or V into omega, by using the relation between linear speed and angular speed, which is your V equals to R omega. How we get that V equals to R omega, that we can discuss. Suppose you have a body which is moving along a circular path with the speed V. So if it is moving along the circular path with the speed V, and its angular speed is suppose omega. So if I consider that it is the circle of radius R, so in a short duration of time, the body, suppose it moves from this point to this, and this angle is, this length is suppose delta L. And the angle subtended is your delta theta. R is the radius. So what we can write for this? This angle delta theta, if you consider, this will be arc by radius, because this one will give you the small angle subtended at the center, and this is your delta L, radius is R. So we can write delta theta equals to delta L by R. Delta L is basically the arc of the circle. So we can write delta L equals to R into delta theta. If you divide it by time delta t, suppose I take the time, it is taking time delta t to move from this point A to the point B. So in that case, dividing by delta t, delta L by delta t, this will be your R, delta theta by delta t. Now, if you take the limit, in that case, what will get? Taking limit as delta t tends to 0. So in that case, it will be your delta L by delta t, limit delta t tends to 0. This is your R, and this is your limit delta t, delta theta by delta t. And this is your V, this is your R. So that will give the expression. Otherwise, this will give you basically what? This will give you the average speed. This will give you average angular speed. And if you take the limit, it will give the instantaneous value there. That means this is giving you the linear speed. This is the angular speed. So this is the relation between the two. Alternatively, you can also take this way also. In one full cycle, what is the length described? In one full revolution, then length of the path described. Length of path described. This is 2 pi r. And if I assume that capital T is the time period and T is the time period of revolution, in that case, speed will be equals to 2 pi r by T. This is your V. 2 pi by T into R. This 2 pi by T, this is the angle described in one full revolution. This is the time taken. So this will nothing but your omega. So this way also you can find. That is another way in which you can get the relation between V and R and omega there. Another simple will be there that you know that arc is arc length. If arc length is angle is equals to arc by radius. So if I consider this as theta, suppose there, and this is your L by R. So L is equals to R into theta. If you differentiate, in that case dl by dt, this will be equals to R d theta by dt. This is your V, this is your R omega. Any one you can use to get the relation between linear speed and angular speed. So now we can get the expression for centripetal acceleration in different forms also. Now what we have derived, centripetal acceleration was your V square by R. Now as V is equals to R omega, this is the expression we have derived just now. That is the relation between linear speed and angular speed. So putting these, A will be equals to R omega whole square by R. That is your omega square R. One R will get cancelled. Or A is V square by R. That can be written as your V into V by R. V square we can write V into V divided by R. Now this V by R is nothing but your angular speed. V by R will be equals to omega. So this is your V into omega. So the centripetal acceleration has the expression V square by R, omega square R, or V into omega. Any one we can use. Depending upon the problem which is given there or any numerical which is given, we can take help of this relation. So this is the expression for centripetal acceleration in the different forms. Let's now see what is the expression for centripetal force. So centripetal force, this will be equals to mass into centripetal acceleration. So this will be mass into centripetal acceleration. So the expression for centripetal acceleration we can write as mv square by r, putting the expression for centripetal acceleration, or it may be your v omega square r, or it may be your mv omega. So these are the expressions for centripetal force on the body, which is there in circular motion. Now, once we have done the expression for centripetal force, because you know that centripetal force, if you consider that we have a body and on that it is the centripetal force acting here, there will be centrifugal force also, which will act away from the center. So centrifugal force, this is equals to minus centripetal force. What does it mean? That it will act in opposite direction. Magnitude wise both will remain same, but the direction will be opposite. Another thing, if you want to write the expression for centrifugal force, then in magnitude, this will be equals to mv square by r, m omega square r, or mv omega. The same way as we have got it for centripetal force. Because magnitude wise it is same as the centripetal force. Only directions are opposite. So it will act in opposite direction. One more thing you remember about the centrifugal force. This is called as the pseudo force. What does it mean? This is the pseudo force. That means this will be the force. We cannot attribute any real force as its cause. These forces will arise only in non-inertial frame. And these will be experienced by the bodies in that non-inertial frame. Suppose you take one example. We have a body moving in a circular path. Or you just imagine that you have a vehicle taking a left turn. Sudden left turn it is taking. The passengers inside that vehicle, they will experience force in the outward direction. Remember, if it is making a left turn, that body needs a centripetal force. That centripetal force will be directed towards the center of that circular path. If it is taking a left turn, the center will lie on the left side because it will be a circle there, and center will be there on the left side of the body which is taking a left turn there. That means it is basically moving in, say, anti-clockwise direction for that particular path. The bodies inside that vehicle, they will be now in a non-inertial frame. Because if the vehicle is taking a left turn, in that case centripetal force is acting. If centripetal force is there, it means it is experiencing an acceleration. If there is an acceleration on a system, then it is not a inertial system. It is a non-inertial system or a frame. So the bodies inside that non-inertial frame, they will experience this pseudo force. So the passengers inside that, they experience the centrifugal force, which will be directed away from the center. So they experience the force in the rightward direction if the vehicle is taking a left turn. It will be just opposite if you take the other turn there. That means if it is taking a right turn, the passengers will experience force in the leftward direction. But also remember, they experience these unbalanced force only when it is taking a turn. The moment after taking a turn, it moves in a straight line path. Then there is no centripetal force required because it is moving along a straight line path. A straight line path you can assume as if this is a circle of a very big radius of infinite value. So if the radius value is infinite, in that case, what would be the value of the force required? That would be 0. So if the force is 0, we don't need that centripetal force there. If no centripetal force is there, that means it is not an non-inertial frame. So the passenger there will not experience any centrifugal force or any unbalanced force there. So remember, centrifugal force will exist or will be there only when the system is accelerating. And that is why it is also called as pseudo force. So far we have discussed only uniform circular motion. But we may have the body which is moving in non-uniform circular motion. So in that case, what will be the net force on the body? What will be the net acceleration on the body? That we'll just discuss. Suppose you have a body which is moving along the circular path, and suppose on that, at any moment, if you consider as it is in non-uniform circular motion, so definitely this time there will be some tangential acceleration. So suppose the tangential acceleration is 80, and there will be definitely a radial acceleration or centripetal acceleration, because that one will be definitely there as long as the body is in circular motion. So this is the radial acceleration. So now the body is experiencing two acceleration, tangential and radial. So the net force on that, or acceleration or the force, will be there given by the vector sum. So the net acceleration is suppose A, and this is at an angle theta with the tangential direction. So if you now consider that AT is the tangential acceleration, so how much it will be? This will be your dv by dt. This is the tangential acceleration. AR, this is the radial acceleration. How much is this? This is your v square by r or omega square r, or anything you can put. Or this is also your v into omega. Next is your A, that is the net acceleration. So A will be given as AR square plus AT square, because the two are in their mutually perpendicular direction there. So in that case, it is your AR square plus AT square. So this is your V square by R whole square plus AT, that means it is your dV by dt whole square. So this will give you the net acceleration. If you want at what angle it is inclined, so tan theta, this is your AR by AT. So that gives the theta as inverse AR by AT. And the net acceleration, if you consider, this is given as your square root of V square by R whole square plus dV by dt whole square. So that will give you net acceleration and at what angle that net acceleration is acting with the tangential direction for the body which is moving in non-uniform circular motion. You may get some numericals like this. It may be given that a cyclist is moving along a circular path and it is increasing its speed at this particular rate. If the radius is this, what will be the acceleration acting on it? So when it is said that it is moving along the circular path and it is increasing its speed with this particular rate, obviously it is the tangential acceleration indication is there. So we can find what is the tangential acceleration. If the speed is given, its radius is given, that means we can easily get centripetal acceleration. So the net acceleration will be given as the vector sum of the radial and the tangential acceleration. So with that, you can get the net acceleration acting on the body. Also, you can get at what angle that acceleration is acting with its direction of anyone, either tangential acceleration or along the tangential direction or radial direction. Of course, this formula is there when it is making an angle theta with the tangential direction. So this is all there in circular motion. Of course, we do all these details of this circular motion, like the motion in the vertical plane and other. When we do the force there and energy concept there, or what power energy we do, after that, all those such cases and the numericals can be discussed. One thing we can notice that if you consider projectile motion and circular motion, in projectile motion, when the body is set into motion, the acceleration due to gravity is acting on the body. That acceleration due to gravity is acting only in one direction. Say if you are taking vertical direction positive there, so it is always acting in the vertical direction. Whatever be the motion of the projectile there, whether it is moving upward or downward, all along its motion, the acceleration due to gravity is acting only in one direction. Of course, it is a constant in magnitude also, as long as you take that the height is not very large, where we can change or we can consider the variation in acceleration due to gravity. So for moderate height there, we can assume that g is constant, and acceleration due to gravity throughout its motion is acting only in one direction, whether the projectile is going upward or downward there. But if you take circular motion, there, even if the body is moving with uniform speed, first of all, velocity will go on changing because it is changing its direction at different points. So velocity is changing even if the speed is constant. Second thing, acceleration is definitely constant in magnitude, but it is also changing. Why it is changing? It's changing its direction. Because if you consider a body which is here, its velocity is in this direction, tangential. Radial acceleration will be there acting on it, which is directed in this direction. The moment it reaches here, velocity will act in this direction. Acceleration is now here at this point. It is in this direction. So here also, if you consider this acceleration is a dash, it is different in magnitude, because direction you can say that it is towards the center, but basically it is changing from one point to other. So in that case, this one will also be changing there in direction, not in magnitude. Magnitude wise, if you consider a1 vector, a dash vector, all will have the same value. Here also v1 vector, v2 vector, whatever we are taking, they all will be same in magnitude, if you consider the uniform circular motion there. So do remember, acceleration is of course here constant in magnitude, but direction is changing there. Also, if you consider for motion in circular path, in that case, if you consider that the body has moved from this point to this, it has subtended an angle delta theta there, and its speed is suppose omega, that will be acting along its axis, angular speed, because there, this is which particular type of vector? This will be your axial vector. We have done the details of that axial vector there, polar vector there. Okay, so you can just revise that so that you can get an idea what is an axial vector, how it is acting, in which direction it acts there. Like for this one, we can again take that if suppose it is making an anti-clockwise direction there, movement, in that case, it will be acting in the upward direction. If it is making clockwise movement, it will be acting in the downward direction there. So for that, you can get the direction of the axial vector also there. So just revise that so that these concepts will also be clear, because these things will be there in this chapter, like angular speed is there, angle is there. So in that case, these axial vector is also important. Of course, we have the speed and the velocity is there, that is the polar vector, so they are also acting there. So make your concept clear about the polar vectors as well as axial vector.